My name is Setliff, and my topic is improving solar panels. One of the main problems with solar panels is how inefficient and expensive they are. Most solar panels have an average percent yield of roughly 18% with the current silicon technology. Roughly 90% of the solar panels on the market today are made by doped silicon crystal structures. One negative of this design is how expensive it is to form the near pure silicon structures that is needed before you can begin the process of doping it. Silicon is also unable to collect a wide range of the sun's electromagnetic spectrum, which is a huge problem with energy efficiency. Another problem with silicon is that it's very hard and fragile. It makes it very hard to transport it to remote locations such as Antarctica. Perovskite crystals are likely to be the future of solar panel technology. The crystals are synthesized to replicate the characteristics of natural occurring minerals. These crystals are specifically made to have very special properties that are useful for solar panel technology. Perovskite crystals can be made into a thin film-like material that makes it possible for the crystals to be painted onto many different substances without losing any of their electric conductivity properties. This painted film also makes the perovskite crystals far more flexible than almost any other material that is currently used by solar panels. Perovskite crystals, according to the experiment, are already proven to be more efficient than all but the highest quality silicon technology. The major flaws of these crystals is that they degrade quickly in sunlight. However, this is not a problem in Antarctica because they also demonstrate self-healing properties when they are given time in the dark, and Antarctica has roughly 6 months of darkness. For our project to be successful, our design must incorporate three important elements. The design must be energy efficient, reliable, and cost-effective. These are very important to our design because if one fails, then our design isn't solving the problem that we want it to. Our design is up to 60% more efficient than the average silicon solar panel. With this increased efficiency, we make our solar panels more affordable because you need less of them to power a facility, and they will pay themselves off in a much shorter amount of time. Lastly, our design is reliable because it will repair itself during the dark months of Antarctica. My idea is to replace the current silicon technology with a more efficient dual-layered perovskite system. Because of the mentioned properties of perovskite crystals, the top layer of the solar panel will be made to absorb a majority of red and infrared light, and the bottom layer will absorb most of the visible spectrum of the solar radiation. IMEC predicts that this new technology will be able to achieve over 30% energy conversion efficiency, which is over 60% more efficient than the current silicon solar panel. Because the perovskite crystals are so lightweight and flexible, they are much easier to transport to the remote and harsh landscape of Antarctica. The diagram on the left shows an aerial view of our new technology looks similar to an old solar panel. And the diagram on the right shows a side view of the solar panel in the two-layered system. So the aerial view of our design is pretty self-explanatory. That will just collect the sunlight. And then what I'm going to explain is the side view. The top red rectangle, that's called the small gap perovskite. That will absorb the infrared and red light. And the blue rectangle called the wide gap perovskite will be used to absorb most of the visible light spectrum. And so the combined output yields more energy than either can alone, allowing for a greater energy harvest than the current silicon systems. So while evaluating my design, I gave my design a 10 out of 10 for costs, a 10 out of 10 for efficiency, an 8 out of 10 for size, a 9 out of 10 for design, and a 5 out of 10 for durability. The reason that I chose this is because I felt like the cost, efficiency, size, and design were all top notch, but the durability is still questionable because it needs to be tested in the climate of Antarctica because it has self-healing properties, but it needs to be seen if these properties can keep up with the damage from the sun. The terms I wanted to define are solar radiation, which is the radiant energy emitted by the sun from a nuclear fusion. Doped, which was when you add an impurity to a semiconductor to produce a desired electrical characteristic. Electromagnetic spectrum is the range of wavelengths or frequencies over which electromagnetic radiation extends. Infrared light is electromagnetic radiation with longer wavelengths than those of visible light. Visible light is the portion of the electromagnetic spectrum that is visible to the human eye. And solar panel efficiency is ability of the panel to convert energy at a low cost and high supply rate.